Hello, students. This lesson will review the periodic trend of atomic size. First, how do we even measure the size of an atom? If an atom has really no definite place where the electrons are, the electron cloud has kind of a fuzzy beginning and end. So how do we measure that? Well, we get very creative and we bond one element to itself. So, for example, two hydrogens. We can measure where the nuclei are. And so if we can measure the distance between two nuclei, cut that in half, we call that the radius of an atom. And we can just call it the size of an atom. You'll see it, of course, it called atomic radius, but one and the same. We just talk about how the size of an atom changes as you move from left to right across the column and then from top to bottom. So do we get larger? Do we get smaller? Does it stay the same size? Same with down a column. There are two determining factors that we must consider when we're predicting the trend of size. One, the strength of the nucleus. Often we use the term nuclear strength. It also can be called nuclear charge. And in second year AP chemistry, we refer to it as the effective nuclear charge. So it gets this Z with a little EFF, in case you see that in your readings. This is the number of protons. It is the electrostatic pull that the nucleus has for electrons. The greater the number of protons, the greater the electrostatic positive pull, the greater the nuclear strength. So calcium, with its 20 protons, has a smaller nuclear strength than chromium with 24. Beryllium, with 4 protons, has a greater nuclear strength than lithium with only 3. So it's the number of protons. Imagine it's the strength of a magnet. So the greater the number of protons, the stronger your magnet. Imagine that, okay? And we're looking at, opposite charges attracting, the positive of your nucleus, the negative of the electron. We refer to that as electrostatic attraction. Just a fancy kind of polished word for opposite charges attracting. So we have to look at, okay, how do we change, or how does the nuclear strength, not that we change it, with how we've ordered the elements, how does that change in the direction we're going? The second thing is, where are the electrons? And if we're talking about the size of the atom, we're looking at the outermost electron. So your nucleus is the electron 1 energy level, 2 energy levels, 3, 4, 5, 6? Is it in, for example, the 3s sublevel or the 3p? Now, usually we're comparing energy levels. There's a minor possibility that you could be comparing different sublevels. Now, we fill the S before P, so we know then that the P sublevel, if it's filled after S, it has a higher energy, which means a further distance from the nucleus. All right, we look at these two things. So, if we examine boron through neon, how about boron through thallium? And so we're looking at across a period, now just the P block, but this will do, and then down boron's family. So our two factors are, what is the change? Remember, an open triangle is change. What is the change in nuclear strength? Are we adding protons, taking protons away? Is it remaining the same? Well, when we go across a period left to right, we are adding consecutively additions of 1, more protons. So the nuclear strength across a period, and I mean left to right, nuclear strength increases. Well, how about down a group? What is the change? And if we just look at aluminum, 13 protons, gallium, 31, well, we are definitely increasing. Okay, but the other thing we have to look at is distance of the outermost electron from the nucleus. Well, boron, electrons are being placed in the second energy level, the p sublevel. But let's just look at energy level. And that's what we're indicating here. So there's no change in electron distance. The electrons are added to the same energy level. And I'm going to say the second energy level. In fact, the 2p. Whenever we can be specific, we want to be as specific as we can be. All right. Well, down a group, oh, look, boron has it in the second energy level, but then aluminum would be 3p, gallium 4p, right? The energy level is equal to the period number. So when we go downward, we are adding electrons to consecutively further energy levels. All right, so if we take a look, in both directions, nuclear strength is increasing. Okay, our nucleus is getting more powerful in its pull for electrons. But across the period, the electrons are added to the same energy level versus down a group consecutively further. So what impact does that have on size? Well, if we could imagine just exclusively looking at, and excuse my definitely not so good drawing of, I'm even challenged with straight lines. All right, so we understand that our nucleus is getting more powerful because it has additional protons. But our nucleus is so small. So we can just, imagine that tiny, tiny, dense positive core. So if we go down a group, and then let's go ahead across our period. Okay. Well, let's talk about down a group first. So we know that our nuclear strength is increasing. However, in the first energy level, we know that electrons, or the first period, are being added to the first energy level. In the second energy level, the third, we have 3, then we have 4, then we have 5. Oh, so even though our magnet is getting stronger at pulling electrons, the electrons are getting further and further and further away. So down a column, atomic size increases. Yes, we're increasing the pull of the nucleus. However, the additional distance of the electrons from the nucleus is what is the dominating factor. So that's all that we have to highlight. The electrons are being added to further away energy levels. You can abbreviate EL. The increased distance from the nucleus equals a larger electron cloud, or volume of the atom. Therefore, the size of the atom increases. So we don't even have to address the increased pull of the nucleus, because it doesn't even play a factor. It's about the further away energy levels. And if you wanted to, draw that, we know in period 2, you're in the second energy level and then the third energy level. So we could do, an example. The electrons in lithium are in the second energy level, in sodium, the third energy level, or something like that. Equals the second energy level. Sorry about that. And then sodium is the third energy level. So greater distance, therefore greater size. All right. Well, now let's think about across a period. So if we want to just look at potassium over to krypton, fourth period, we know our nuclear strength is getting greater and greater and greater. But we're adding the electrons to the same energy level. The same energy level. Now, of course, once we get the D block, this is 4s3d, very close in energy. Even though these are assigned to a lower energy level, we're still not adding energy levels, because, you go to the 3d, but then back to the 4p. So across a period, the nuclear strength is the predominant factor. All right. So across a period, actually, atomic size decreases. Now that contradicts our common sense. So why would that be? As move right in the same period, the nuclear strength increases as atomic number increases. And electrons are being added the same distance from the nucleus. The same energy level. Therefore, the greater pull of the nucleus for the electrons results in a more compact, electron cloud, which means a decrease in size. So if we could imagine, as we're going left to right, so potassium has 19 protons, calcium has 20. And then let's jump to zinc, which has 30. And then how about selenium? That has 34. Well, this nucleus pulling for the fourth energy level will have a good pull. But then as we add one more proton, it is going to pull more strongly on that fourth layer of electrons, resulting in, I'll just use your imaginations, please, resulting in slightly smaller atom. And then how about 10 more protons to the same distance? Well, then that's going to lead to an even smaller, add 4 more protons to 4 layers of electrons. That's even going to be smaller. So a visual, as we proceed down a family, we get larger because of increased energy levels. As we move to the right, we get smaller. The energy level does not change, but the nuclear strength does. The increase in nuclear charge can or does result in a greater attraction for the same layer of electrons. Therefore, it's a more efficient pull, resulting in smaller atoms. Here are actual numerical values. I bet these are angstroms, but we can see, oh, I know that's a little bit unclear, but you can just look visually at what we're talking about. And here's just another. So now this is saying orbits, we know energy levels. Oh my gosh, and not orbits. That's going back to Bohr, but shells are energy levels. So we increase layers. Here, no increase, but in layers, but an increase in the strength of the nucleus. Another visual for us. So we know our great blocks of the periodic table. Well, if we could use this schematic, going downward, we're adding more and more and more levels, layers of electrons, where across they're the same. And so your atoms are going to get pulled, or your electrons are pulled more efficiently by that more positive nucleus. Okay, ladies and gentlemen, so truly understanding the trend of atomic size makes all the other trends just fall into place. We need to make sure that we are thinking about, okay, what's going on with our nucleus? And then where are our electrons? That makes all the difference. Best of luck.